you doing, Tony? We're the A team and we're here to talk about our project, which is on projectile motion. And what we're going to do is Warren and I are going to hold a water balloon launcher, launching a tennis ball at equal height. And what Tim is going to do is he's going to pull it back and make sure that it's a 45-degree angle, which he will explain, and launch the tennis ball. Here's Tim to explain the 45-degree angle.
Alright, so to make sure that it's going to launch at a 45-degree angle, what we're going to do is Warren and Greg are going to hold the water balloon launcher at 50 inches above the ground, and I'm going to pull it back 50 inches behind where they are, which if you do the trigonometry, it'll give us a 45-degree angle right here. And when transferred over to this diagram, because these lines right here are parallel, this angle gives 45, and so this angle will also be 45, giving us our launch angle. And now Warren is going to talk about the rest of this diagram.
Okay, so Tim talked about our isosceles triangle with the 50-inch measurement here. What we're going to do with that is someone's going to have a stopwatch. Once we release the ball here, they're going to start the time, and then once it hits the ball and covers this distance here, they're going to stop the time. What we'd be able to do with that is apply it to our motion equation here. Now we know that because of the deceleration from gravity at the top pinnacle, or the top of its y distance, the velocity of the ball is going to be 0. So the initial y is going to make this whole part of it 0. Now, with our total time, we're going to have to use half the time, because as you can see, what we're going to use is from the max height to when it hits the ground. So we're going to do 1/2 gt squared. That'll give us our max height. However, the velocity we're trying to calculate is once it actually leaves the launcher, that point right there. So what we're going to have to do is subtract our 50 inches. Well, first we'll have to convert it to meters, because this is going to give us meters since gravity is in meters per second squared. So we're going to have to convert this to meters, subtract it from our y1, or our maximum height from the ground, and then what we'll be able to do is apply that height to this equation to figure out our final velocity, because this initial velocity, of course, is going to be 0.
Good.
Alright, we're here to do some projectile motion, and just to get straight into it and skip all that other stuff, we're going to come over here. We have a water balloon launcher right here, and we're going to measure this height right here to each hand as 50 inches to each spot. So you want to drop up. Okay, don't move. And then over here again, at a 50.
This should be the bottom of the grip.
Down. Right there. Alright. So now our height is going to be 50 inches. And now, this bottom length right here, we're going to do 50 inches again, which gives us an isosceles triangle.
With a 45-degree angle.
Yes. Yeah, which means that this angle right here, where this thing is going to come up, is going to be 45 degrees. So that way, we know that the angle this thing leaves above the horizontal is also 45 degrees. Fire nuke. Greg over here is going to be recording our time.
Countdown.
3, 2, 1.
Oh.
3.9 seconds.
2 more feet to the right, Tim.
You write down 3.9?
Gotcha.
Whatever.
Wait.
Okay.
3, 2, 1.
.9 seconds.
after Tim launched the water balloon rocket 4 times, we recorded all of them. Then we took the average of all 4 so that we'd only have to do 1 calculation. And since we're calculating the height using the velocity initial as the peak of the arc and making that 0, we also have to cut the time in half since we're only using half of the projectile. So over here, I've taken our average time, divided it by 2, plugged it into the equation over here, square it, multiply it times the acceleration, which is gravity, 1/2 plus 0, and we get 18.16 meters for the top height of our projectile of the tennis ball.
Cool. So, then we also use this other motion equation here to find the the velocity of the y direction. That was very funny. Thank you, Greg. By using what Katie found here as 18.6 meters was our total height in this lovely graph that we showed here. But we also noticed that the tennis ball didn't leave the slingshot until it was at least 50 inches up. But we're working in meters, we don't want inches. So we transfer the inches to our lovely equation here, and we get 1.27 meters. So taking that as our distance that it actually leaves, we take her height, subtract that height to get 16.89 meters for our initial velocity height. Plugging this in, we get 2 times the gravity times our new height. Square root it, because this is squared, to get 18.2 meters per second for our y direction.
Alright, so while Tim gets ready to show you how we're going to use that vertical final velocity, I'll explain to you a little bit about what it actually is. So, if we neglect air resistance, we can assume that the flight path of the ball is symmetrical, even though we didn't draw it very well or to scale. So, what we found using those equations that Tim raised, we have our V final here at 50 inches above the ground. So we have our V final here, and since it's 50 inches above the ground here, we can say that this V final is actually this V initial. Now we're waiting for Tim.
Alright. So we're going to come over here, and we're going to use vector addition, because this right here is going to be our vertical velocity of 18.2 meters per second. This right here is going to be our theta of 45 degrees right here. And we know this is 18.2 meters per second. This is going to be our horizontal velocity. And they're going to be equal because of the properties of a triangle. This is also going to be 18.2 meters per second. And if we use Pythagorean theorem to find this side, which would be the resultant vector, it's going to give us our total velocity of the initial launch. So a squared plus b squared equals c squared. Pythagorean theorem. So just plug these numbers in. We're going to get the square root of 18.2 squared plus 18.2 squared equals C. Our answer, 25.7 meters per second.
With our space fitting.
Right there.